So welcome everyone to this week's QTFMS seminar. Uh, Today we are pleased to have Yunqin from Calvin Institute of China, Beijing. He's going to talk about his recent work on continuous non-invertible symmetries. So Yunqin, thanks a lot for accepting our invitation. You can take it on.
Thank you very much for inviting me here. And it's a great series of seminars, and I enjoyed a lot from the previous ones. So today I'm going to tell you about our recent work on continuous non-invertible symmetries. This work is based on this paper in collaboration with Diego Demastro and Adar Sharon, who are fantastic collaborators. And yeah, if I do not have time to explain everything about this work, please refer to the paper. So the outline of this talk is as follows. So first, I'm going to give you a brief motivation for why we are interested in this problem. And then I'm going to give you a simple example of continuous non-invertible symmetries, which people have already been known for quite a few years. And then I'm going to discuss a generalized version of the Noether theorem, which allow us to find new examples that beyond this type of example. And then I'm going to use this generalized Noether theorem to find more examples, more non-trivial ones, and possibly I'll have time to discuss one application for that. Okay, so this is the outline. So let me begin with the motivation. So the central idea of the generalized symmetry which developed in recent years is that we should think of the generalized symmetry as the topological operators or topological defects. I'm not going to distinguish the operator versus defect because I'm not working on the lattice in this talk. So I'm going to use these terminologies interchangeably. So this idea has been very successful in maybe the past decade, especially in the case when we consider the finite symmetries, namely there are finite number of symmetry elements or symmetry objects. So it's very successful for finite symmetries. And yeah, as you know that there are many two generalizations, which we call the higher form and non-invertible symmetries. So they are it's successful because it leads us to many physical consequences. For example, we can use it to construct many new lattice models. Especially in recent, like in the past months or so, people have been able to construct a new lattice model that flows to the critical point between the two different phases. It's also very important in our understanding of new understanding of phases and phase transitions. So this comes with the name of the generalized Landau paradigm, meaning that we can organize different phases using the different patterns of symmetry breaking. But now, because the notion of the symmetry gets generalized, so previously what we thought to be like lies outside of the Landau paradigm now we can include them inside the new generalized non-dot paradigm. So it helps us to organize, give a more complete organization of the phases and the phase transitions. And then yeah, it also provides us new RG flows, RG flow constraints, etc. One of the reasons that these finite symmetries are like the generalization in terms of the finite symmetry, in the case of the finite symmetry, is very successful, is that there is a solid or relatively solid underlying mathematical framework, like a mathematical foundation for these symmetries, which is that these finite symmetries are described by the fusion categories. And because like in the math community, the fusion category or a higher fusion category has been studied for quite a while. So the physicists can use their results and borrow their results to understand the finite symmetries. Okay. Now, and then it comes with the question that how about the continuous symmetries? This is a very natural question because like for the ordinary symmetries, when we first learned ordinary symmetries, probably the first example is the continuous symmetry, right? For example, the space rotation or the charge conservation, etc. So all of these are continuous ones. And in when we learned the continuous symmetries, especially in the quantum field theory 101, we are all also taught that the continuous symmetries, well, okay, yeah, before that, so let me say a few remarks. So first of all, how should we think about to generalize the continuous symmetries? Well, for continuous symmetries, if we follow this like a general philosophy, then what we need to do is just to copy this philosophy. So just a copy this correspondence and add a continuous on both sides. Well, by continuous topological operators, I just mean that the operators are labeled by a continuous parameter. Right? So this is a very straightforward generalization. But the question is, can we find examples in like quantum field theories that exhibits these continuous topological operators? It's not very obvious that where shall we look for them, right? And and so this is a hard question in general. But on the other hand, when we first learned the continuous symmetries, especially in quantum field theory 101, we are also taught that there is a Noether theorem. And the Noether theorem told us that the continuous symmetries, so ordinary or conventional continuous symmetries. By conventional, I just mean that it's a zero form and it's invertible. They come with a local conserved current. Usually we just say that it's a conserved current and we just don't bother to mention that it's local because it's just a local operator. It's just a current mu defined on an arbitrary space-time point. And it's conserved because partial mu j mu equal to 0. Well, this can be generalized to higher form symmetries as easily, straightforwardly, just by putting more Lorentz indices here, anti-symmetric Lorentz indices. But the question is, like, how about the non-invertible and continuous symmetries, namely, so how should we generalize this Noether theorem? Like, is there a Noether theorem for that? So this is one of the main question. And the upshot of this talk is that indeed there is one. So let's call it the generalized Noether theorem. Meaning that the continuous non-invertible symmetries also come with the conserved current. But this conserved current is not local. It's a non-local conserved current. And later I'm going to clarify what do I mean by this word non-local. Yeah, but this is the slogan. Okay. And the point of this talk, the goal of this talk, is to explain this correspondence. And once we understand this correspondence, we can try to use it to help us to find new examples of the continuous non-invertible symmetry. Okay, so this is the idea. And I have to remark that we are not the first one to discuss this correspondence. In fact, there have been already quite a few discussions alluded to in many places. So, for example, this correspondence was alluded to in this paper from 21 by Yifan Wang and Ran Sangren in 2021. And also, it's also mentioned in a talk by Shuhen Shao in Simon's Club, Simon's Simon Center, also in 21. Yeah. Yeah, but the goal of our work and also for this talk is to discuss this correspondence more systematically. Okay, so this is the basic motivation for this talk. So are there any questions about the motivations?
I have one question about this
Yeah.
generalized Noether. So let's say we have a global symmetry that is associated to a group. We can always couple to some gauge field, like background gauge field of the curve, and then gauge the symmetry to get a Yang sphere.
Yes.
When we have a infinite tensor category as a symmetry, can we also do that using this generalized Noether space?
That's a good point. I think the answer is yes and no. So maybe let me briefly explain this. So let's recall the ordinary symmetry. So for the conventional ordinary symmetries, so we can insert a defect. So for example, we can talk about the symmetry operator. And the symmetry operator is supported on some codimension 1 surface, right? And if we insert this symmetry operator into the path integral, so we can write this operator as this a like star J, wedge star J, where A dictates the location of this manifold, which defect lives on, right? So from this perspective, yes, because we can still design, so we can still write down an expression for this gauge field, which is just indicates the location of this defect. Yeah. But you may wonder like whether it's useful or not. Like whether can we use it to do some computations? And the answer is, well, we don't know so far because we haven't like looked very deep in this direction. But maybe, hopefully, it will be useful. Yeah.
I see. So by just choosing A to be some Poincare rule of this part,
Yeah, yeah,
we can do
yeah,
the same
yeah,
thing, but it's not
yeah,
clear if
yeah.
we can gauge it to introduce some
Yeah,
categorical
that
constraint.
part, well, for gauging, like in terms of a defect, you also know that what do we mean by gauging, right? In terms of defect, we just insert a mesh of this defect in the path integral. Yeah. Optimistically, I think that we can still discuss the gauging in terms of the gauge fields. But practically, how do we like figure out all the details? And then that's another question. Yeah,
Like, is there a Lagrangian for it, for example?
yeah, 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 yeah. And like discuss the counter terms and discuss the gaugings, the twisted torsions, etc. Yeah, all of those details we haven't figured out. Yeah.
Okay.
All right. So so this is the motivation. So let me give you a very simple example, which is the second part of the talk. So a simple example, which is the cosine symmetry. This symmetry has been known for quite a few years, but we found the recent work by Theo Jacobson from last year, and also by work in a work by Kobayashi, also by Poshen Xing. Let me see. Also by Caroline Zhang, also from last year, and another work by Weiguan Cao, Yuan Miao, and Masahito Yamasaki from early this year. So we found these works to be quite helpful. Although like the discussion of this cosine symmetry has been known for quite a few years, maybe 10 years. So let me so explain what do we mean by this cosine symmetry. So let's consider a 1+1D QFT, maybe the CFT with U1 symmetry, and also the charge conjugation symmetry. So for U1, so this is just ordinary symmetry. It comes with the local conserved current. And we can construct a topological operator or topological defect by this standard construction. And I'm also going to denote the topological operator for the Z2 charge conjugation as eta. Okay. And the reason that why I call it just charge conjugation, not just a random Z2 symmetry, is because this Z2 symmetry has a non-trivial interplay with the U1 symmetry. And the interplay is that the Z2 symmetry flips the charge of the U1. So, or it flips the charge, and also it flips the current. So it gives the current a minus sign. Or in other words, the current of the U1 is charged under the Z2 charge conjugation. Okay. And in terms of the defect, so they satisfy this non-trivial commutation rule. Yeah, so this is also obvious. Okay. Um, so far we only discussed a very simple theory with these naive symmetries. And oh, by the way, so to have an example on the back of your mind, um, you can think about this example. So there is a compact boson in 1+1 dimensions, whose action is r over r squared over 4 pi times d phi d phi. And the U1 symmetry is just a shift symmetry. And the Z2 charge conjugation is flips the sign of phi. Yeah, so this is the a concrete realization of these symmetries.
Can I ask a question?
Yes, yeah,
So
please.
in the first example you discussed, we had a U1 symmetry with Z2 with a mixed Hofft anomaly, but in the second one we
No,
have two
no,
U1s. Sorry,
sorry. So there's no mixed Hofft anomaly. So why do you say that there's a mixed Hofft
because
anomaly?
the Z2 acts on the topological defect of U1.
That's
Isn't that
right.
an
But it
anomaly?
just means that there's a non-trivial symmetry algebra. So it means that the symmetry, the total symmetry, is not U1 times Z2, but it's a U1 semi-cross Z2. So the symmetry
Okay.
structure is U1 semi-cross Z2. And it's just
Okay.
it's just a statement that the symmetry like group, the symmetry group is a non-trivial, it's not a product group.
Okay,
It
okay.
doesn't say anything about the anomalies. Yeah.
Okay, okay, sorry. Yeah,
And
that's right.
yeah. And in this example, as you said, that there are two U1 symmetries, indeed, but we can focus on one of them. So in here, I'm just focusing on the shift symmetry, momentum symmetry. But you can also talk about the winding symmetry, and the story will be the same. Yeah.
Okay. But what I wanted to ask was that in the first case, if we gauge the Z2, we get like a
Yes,
O2 gauge group, right?
that's right. That's exactly the point I'm coming into.
Okay.
Yeah.
So I was thinking of what happens in this compact program if we gauge the Z2 conjugation, like which
Yeah, yeah,
U1
yeah,
becomes
yeah.
the O2.
I'm getting that. Yeah, I'm
Okay.
getting that. So yeah, just hold on. So yeah, so these are very simple theory. So exactly. So we are in order to get a non-trivial example of the symmetry, which is the cosine symmetry. So what I'm going to do is to gauge the Z2 charge conjugation. So let me call this CFT to be Q, and I'm going to gauge the Z2 charge conjugation. So after gauging the Z2 charge conjugation, oh, by the way, so before gauging, the symmetry is O2, yeah, as you said. So then we should ask, like, what is the symmetry structure after gauging? So if we are like a naive person and we only look for the symmetry described by a group, so we should look for the symmetry operators, which are unitary operators. And because we already gauged the Z2's charge conjugation, so the original charge conjugation is gone in the gauged theory. But you may also know, as you know very well, that there's a quantum symmetry. So there is a Z2C hat quantum symmetry, which I denote the symmetry operator as the eta hat. Okay, so this is the quantum symmetry, which is well known. And then how about the U1? For the U1, if we only focus on uh, the, the symmetry that described the group, so we should look for the unitary operators that commute with the Z2 charge conjugation so that they can survive under gauging. So, so the operator that commute with the charge conjugation from this expression, it's clear that the only operators are either the identity or the U alpha equals to pi. And this guy is generates a Z2. It's an order 2 operator, and it generates the Z2 symmetry. So naively, uh, yeah, if you only focus on the like ordinary group-like symmetries, then you would conclude that the symmetry after you gauge, so when the symmetry you get after gauging uh, is just a Z2 and times the Z2 hat C. And the original U1 is gone. So the U1 is gone. But so as we already said that in the beginning that we should really consider all possible topological operators as the symmetries. So namely, we should not just look for unitary operator, but also the possibly non-unitary operators. So what are the non-unitary operators that still commute with the charge conjugation? Well, so we can look for this combination, U alpha equals to U plus U minus alpha. And this operator clearly commute with the eta because eta exchanged these two guys. So so let's give it a name. So let's call it N alpha. So it commutes with eta. So it should survive under gauging eta or Z2 charge conjugation. Yeah. And this is what people call the cosine symmetry. This is because the U alpha equals to U e to the I alpha integration of the star j, and plus U e to the minus I alpha integration of star j, which is just a 2 times cosine alpha times integration of the star j. And because this N alpha takes the form of the cosine function, so that's why it's usually called a cosine symmetry. Yeah. And one property of this cosine symmetry is that it satisfies, say, non-invertible fusion rules. So N alpha times N beta, so N alpha plus beta plus N alpha minus beta, and also N alpha equals to N minus alpha. Yeah, so these are the two key properties of these non-invertible symmetries. Yeah, so are there any questions about this so far? Okay, so so this is the understanding, like before last year, but this paper, these papers very nicely pointed out that there is a problem with this construction, and the problem is that this operator, this naive operator, this operator is actually not a very well-defined operator in the gauged theory. The reason is that this operator, although it's invariant under the global charge conjugation transformation, but it's not local. It's not proven to be invariant under the charge conjugation gauge transformation, because in this theory we already gauge the charge conjugation. So this operator is actually not gauging invariant, although it's a global invariant, invariant on the global charge conjugation transformation, but not gauging invariant. So that's not quite well defined operator. So how should we construct the operator that is gauging invariant under the charge conjugation gauge transformation? So that's what these papers are addressing. And the idea to find the correct operator is as follows. So you have a theory Q, and you have this U1 symmetry operator, U alpha. And then you would like to find like what this operator becomes after gauging. So the gauging operation can be also be implemented by the gauging interface. Yeah. So for example, instead of doing the full space gauging, so which maps the Q to Q mod Z2C, instead we can consider an interface or topological interface between these two series. And let's call it N. Well, maybe let's call it D. And how should we construct this topological interface? Well, it's quite familiar in recent, like it has been used quite a lot in recent years because we just do the half space gauging with Dirichlet boundary condition imposed at the interface. And this is precisely how people construct the non-invertible duality symmetries in the case when these two sides are equal, like are isomorphic. But here, the Q and the Q mod Z2 are not necessarily isomorphic, and in that case, we get not the duality defect, but the duality interface between the two sides. Okay. Now, so in order to get that, like see what is the consequence of this operator after gauging, after do the gauging the charge conjugation, what you need to do is just to sandwich this operator using the two gauging interfaces. So you have D here, you have D dagger here. And the theory on this side is Q mod Z2 C. On this side is also Q mod Z2 C. And because this interface, like these interfaces are topological, so we can make this slab to be very, very thin. And effectively, it will become an effective operator within the Q mod Z2 theory. So we should treat this whole thing as an operator in the Q mod Z2C theory. And this operator is what this whole thing is what this U alpha becomes after you gauge the charge conjugation. Yeah.
Can I ask a question very quickly?
Yeah, sure.
So you're
Sure.
essentially considering a condensation defect with some U twist, like, right?
Yes,
If you didn't have any U, it would be the
Yeah.
condensation, but now you have the U.
Exactly. Yes, yeah.
So you're higher gauging the Z2 on this codimension. Is that correct? Or
Say again.
so you're essentially gauging this Z2 symmetry on the codimension one because this is like a condensation defect.
Right. Yeah. And yeah, more precisely, yeah, that's right. But the way I would want to interpret it as is that I should gauge the Z2 in a thin slab and then take the thin slab limit. You will see why I want to do that in a moment. Okay. And this is what this should be really the appropriate definition for the for this cosine symmetry on alpha. And using this definition, you can easily verify that this on alpha also satisfies this fusion rules. So this fusion, the fusion rule that I mentioned earlier. Yeah. Okay. So this is the appropriate definition, and this is in the literature, it's called the sandwich construction. Good. Okay. And on the other hand, let's ask where are the currents? So you know that before gauging, it's just an ordinary U1 symmetry. So we should think of it, there should be a current associated with this U1 symmetry. Then we can use this gauging construction, like a sandwich construction, to see what this current becomes after gauging. So this is also a nice illustration of where the current, non-local current comes in. So before gauging, you have a current J. And after gauging, what you need to do is just to impose like a sandwich this J between these duality interfaces. D dagger and D. And then because this D is topological, so you can gradually move this D toward the left and try to collapse with the D dagger. However, you have to pass through this J. So what happens when D pass through J? Well, in the beginning, earlier, I said that J is Z2 symmetry. So under Z2 charge conjugation, J gets mapped to minus J. So which means that J is an order parameter. Of the charge conjugation. Okay. So J is charged on the charge conjugation. Now this D is a gauge interface. So it gauges the Z2 charge conjugation on one side. So when you move this D pass through J, it's so then it's not hard to see that this J becomes a disorder parameter on the other side. So this is D dagger D. This is quite like the Ising model, where you have an order parameter in the Ising model, but in the dual Ising model, which you get after gauging the Z2 symmetry, you will get a disorder parameter. And the same thing happens in here. So the order parameter on one side of the duality interface becomes the disorder operator on the other side of the duality interface, right? And the disorder parameter just means that this J in the Q, so on this side is Q mod Z2. So only this disorder parameter is attached to the quantum symmetry line in the gauged theory. Okay. And then if you further collapse these two duality interfaces, you will just get a condensation operator, 1 plus eta hat attached to eta hat here with a J. And now you see that this J is no longer a local current in the gauged theory, but it's a current attached to a topological line in the gauged theory. And that's what I really mean by the non-local current. Non-local current just means it's a current attached to a topological line in a gauged theory. Yeah. Okay. Now we see that in this particular example, let me see. Okay, so yeah, before talking about that, so this is the end of the discussion for the cosine symmetry. But as you can see that this construction can be generalized easily to many other cases, right? So and this comes with the name of the coset symmetry, or maybe the double coset symmetry, which is that if you start with a continuous symmetry G, which is continuous, and you can gauge a non-normal subgroup, finite normal subgroup, and then the theory after gauging the this H symmetry is a non-invertible symmetry. So this guy is non-invertible. And because G is continuous, so it's a non-invertible continuous symmetry. Okay.
Can I ask a question?
And yeah, go ahead.
So what you're essentially saying is that the non-local current operator is a non-genuine operator that ends on some topological line.
Yes, yeah.
So But I'm assuming that here you assume there are no topological local operators in the theory.
Yeah. I'm
So
assuming one vacuum.
yeah.
Right.
So if you have like topological local operator, then at the
Yes.
junction, you may have something interesting happening. Have you considered that scenario? Like what can happen if you have like a -1 form symmetry and then the topological line just changes at the intersection
You mean
point?
one form symmetry? You mean one form symmetry?
-1 form.
Because
Uh,
no, topological operator is a generator for the one form symmetry in 2D.
sorry. Yeah.
Oh
I'm
yeah,
sorry.
okay.
Yeah.
So I get
Sorry.
your point. I get your point. So yeah, it's a very interesting point. So when you have a one form symmetry, then there are several interesting things that you can think about. One is that once you have this configuration, then you can try to stack a topological local operator at the junctions. So you can modify the junction. So which means that once you have a J attached to a line, you can use it to construct more than one symmetry topological operators, like because you have more than one choices of the junctions. So this is one thing that you can play with. Another thing you can play with, which I haven't thought about it before, is that you can imagine a situation where this eta line, this eta hat line, can terminate on the local topological operator.
Okay, yes.
So so you have on one hand, the eta line can terminate on J, but on the other hand, the eta line can terminate on the topological operator O. And because this side is topological, so you can shrink it away, right? You can shrink it to make it a local operator. So that's also one scenario that can happen. Yeah.
But in that case, we would essentially have a invertible symmetry, because the
Yeah,
current is a local
That's
operator.
right. That's right. Yeah. It would be interesting to find an example which realizes this scenario. Yeah, I haven't thought about it before, but that's an interesting point.
I see. Okay.
Good. Okay, so let me see. Okay, so we see that we have a very systematic way to construct this the continuous non-invertible symmetry using this gauging construction. But you can ask, like people can ask whether this is useful or whether this is interesting for some purposes. So for example, from the purpose of considering the constraints of the RG flow, this construction does not seem to be quite useful. The reason is that the RG flow commute with the discrete gauging. So it means that whatever you learn from this non-invertible symmetry in the RG flow, we can always trace it back to the ordinary G symmetry before gauging, and study the RG flow over implication of the RG flow there, and do the gauging back. So this type of the symmetry which come from the gauging does not seem to be very useful for the purpose of finding new constraints on the RG flow. Yeah. Although this symmetry might be more natural to consider this non-invertible symmetry in some framework where the RG constraint on the RG flow is more natural, but nevertheless, you can always trace it back to the other side where the symmetries are invertible and study the constraint on the RG flow there. Okay, so this is one one point where this symmetry or this construction is not very appealing from the perspective of the RG flow. Okay, so the question then is, can we find more examples beyond this gauging construction? And and also earlier on, we see that so in this cosine symmetry example, you have a non-invertible symmetry N alpha, and at the same time you have a non-local current. But like, do we see like do they appear together just because it's a coincidence? Like, do they appear for a reason? So in other words, the continuous non-invertible symmetry and the non-local currents uh, uh, do they uh, do they always appear together? And is there a relation like an intrinsic relation between them? So, and this is basically the what the generalized Noether theorem is about. And that's the point that I'm going to explain in the next part. Okay. So this is a generalized Noether theorem. All right. So now, in order to explain this correspondence, so we just need to explain the arrow toward the right and arrow toward the left. Okay. So for the arrow toward the right, this actually has been already discussed in a paper by Ran Sankaran and Li Fan Wang. From 21. So we can borrow some results over there. So let's start with operator. So let's call it an alpha, which is labeled by a continuous parameter. And in this paper, what they have shown is that there is a 1, 0 or 0, 1 local operator, which we call J, living on this N alpha. The basic reason is that this operator, because it's labeled by a continuous parameter, so it better have a exactly marginal operator living on this operator, for which when you turn it on, you can like move in this manifold of alpha, right? So there's exactly marginality means that its scaling dimension must be 1. And also, the spin of the J must also be 1, which follows from the fact that this operator is topological. And together, if you put a condition that the spin is 1 and the scaling dimension is 1 together, then it constrains that the conformal weights must be 1, 0 or 0, 1 in of this local operator living on the line. Now, we haven't used any information so far about the invertibility of this topological line. So, how do we see that whether the non-invertible property comes into play? So, in order to see that, we can fold it on alpha along the locus of the J. So once we fold it, then we can first fuse this middle part. After fusing this middle part, then we get a configuration like this. And with an intermediate channel L. Yeah. And then we can shrink this bubble and get an effective J. Yeah, maybe let's just call it effective. Or yeah, just to not clutter the notations, let me just call it J. Okay. Now, then you see that there is a J living at the end of some topological line L. But so, and So when in a special case, when n alpha is invertible, then this L must be identity, right? Because n alpha times the orientation reversal of the n alpha must be 1. So that this channel can only be identity. So which means that this bubble is like isolated from the rest part of the diagram, and you get a local current. So and that reproduces the ordinary conventional Noether theorem. So the invertible symmetry gives the ordinary local current. But when an alpha is non-invertible, then there are more than one channels, there are more than one channels. In particular, there are non-trivial channels in the middle, and there should be some current living at the end of some non-trivial topological line L. So that basically explains the right arrow, which is that the existence of this continuous non-invertible symmetry implies that the existence of the non-local current J living at the end of some topological line L. Now, how about the other direction? Well, in order to see the other direction, let's first recall. The invertible case. So in the invertible case, let's recall that how do we construct the topological operator from the current? Well, what we are instructed in the quantum field theory is that we first construct a conserved charge out of the conserved operator, conserved current. And because the conservation of the current, the charge does not really depend on the shape of the underlying manifold gamma. And then you just exponentiate the Q of gamma. And it will give you the conserved topological operator. But you may wonder why, we are only interested in this special form of so a special form of this operator. So in other words, why can we don't consider an arbitrary function of the conserved charge? This is also topological because the Q is topological, this Q is independent of the shape of gamma. So an arbitrary function of Q should also be independent of the shape of the gamma. So it should also be a topological operator. But why we don't consider that in the quantum field theory? The reason for this is that a generic function or arbitrary function of Q, of the conserved charge, it does not satisfy, does not give us the well-defined notion of the diffactible space. So for example, if we orient the Q, orient this gamma along the space direction, it will give us an operator. But if you orient the gamma along the time direction, it will give us a defect. But for generic function, it will not give us the well-defined notion for the defect Hilbert space. And only this special form of the function of the Q will give us a well-defined defect Hilbert space. This is because, well, in the action, so how should we think about this special form of the function of the conserved charge? So we started with the action. We just, in order to turn on this topological operator in the position function, we can deform the action by adding this action in a source term. And maybe it's more easy, it's more comfortable to write it in terms of the A star J, which we mentioned earlier in the talk. And then this construction automatically ensures that there is a well-defined defect Hilbert space, but because you can easily, orienting this gamma along the space will give you the operator, and orienting the gamma along the time will give you a defect, well-defined defect. And And then in the path integral, so you just do this. Well, maybe let's do it in the Euclidean signature. Then in the path integral, this is nothing but the correlation function for the alpha star j count. Yeah, with possibly other operators inserted. Okay, so the idea to generalize to this non-local current is very similar. So what you need to do is to consider what you need to do is just to slightly modify this construction a little bit. So this construction, so in order to construct a topological operator out of the non-local current, you first need to consider. First of all, this non-local current is attached to a line L. And then you will first have to worry about what happens at the other end of the topological line L. Well, we can find an arbitrary topological line B, which we call the baseline. And the choice of the B is such that there's a non-trivial topological junction. So it's a topological between the B and L, B and L. So as long as there is a topological junction, then you can form you can consider such a configuration, and then you can form a loop of B. And then you can integrate this J over this loop, right? Okay. So now it's clear how to generalize, how to construct the topological operator. Basically, what you need to do is that in the path integral, you first insert a base loop P, or maybe a circle of the base loop. And then you insert you consider a line, J, attached to B with a topological junction X, and you integrate this J over the base loop B. So you just do the integration, J star J over the base loop. And this gives you the this gives you the topological operator. So this topological operator basically takes the form of B times the e to the I alpha star J. Yeah. But this is, but what we really mean is that we integrate this J on the base loop B. So this notation is just a schematic because the interpretation of the product between the B and its exponential expression is that we should integrate this J over the base loop B. Okay, so is there any question for this construction?
Yeah, I have one question. So
Yeah.
if we think of a categorical symmetry that is non-abelian, the integral seems a bit tricky. We have to define some path ordering maybe.
Exactly,
I mean,
exactly. Yes. Yeah.
How is that resolved?
Yeah. So indeed, so you really have to do the path ordering of this J. So and the detail is in our paper. So we should really have to. So first of all, in this case, yeah. So it's really that we have to do the put a path ordering for this integral J. Yeah, it's really hard to explain here, but maybe you can look at the papers. Yeah. And yeah, there are more subtleties. For example, you may need to worry that this L can act on this J non-trivially. So this is also another reason that doing the path integral is necessary because it avoids the action of the L on the J. Yeah, otherwise you have to like consider the switching the position of the different j's will make the L act on J, and then you may encounter some trouble. But after you assign the path ordering, then all of these subtleties are gone. And this is uh, the key point to prove that that the operator is topological. Yeah.
And
Okay, so
is this naturally encoded in like Berlin algebra of some non-abelian WZW models? Like this setup
yes,
and the
yeah.
path ordering and so on. Is it naturally encoded?
Uh, you can find an example. So later on, I'll give you an example of the Wess-Miller-Witten model, which exhibits these symmetries.
Okay.
Yeah. Okay, so right. Okay, so this is a definition of, so this is how do we construct the topological operator from the non-local current. Okay. Let me see. Okay. So, and then you may wonder, so this is a definition, and I told you that it should be topological, but you really need to prove it that it's really topological. And for that, what we need to do is to compute this correlation function. So let's call it an alpha to 0 and an bar alpha to 0. And if you define this operator properly, and it turns out that these equations will, like these commutations will vanish, which shows that this operator are topological. Okay, good. So now, so this basically finished the discussion for this direction. So we have already finished the generalized Noether theorem, which means that the continuous non-invertible symmetry can be associated with the non-local current. Okay. Now, once we have this Noether theorem, we can try to use it to help us to find new examples of the continuous non-invertible symmetry. So finding continuous non-invertible symmetry just amounts to finding the 1,0 operator in the twisted sector or attached to some line L. J attached to line L. And it turns out that there are like this operator exists ubiquitously in many CFTs in 1+1D. So I can give you a list of examples. And the simplest example is the C equals to 1 CFT. And so in this CFT, so it's well known that C equal to 1 CFT can be organized in a modularized space where this horizontal axis is the orbifold branch. Oh, sorry, is the circle branch. And the vertical axis is the orbifold. And in this point is the self-dual radius. So it's called R. So it's R equals to 1. And is described by the SU2 level 1 Wess-Miller-Witten model. And there's a point which is related to the Dirac fermion, which is the square root of 2. And this is the KT point. And there were also 3 exceptional points which are not discussed in this talk. And earlier, so and these the circle branch and the orbifold branch are related by gauging the charge. So for the second part, we already see that on its vertical axis, and they are the cosine symmetries. They are precisely the cosine symmetries because this in theory on this axis there is a U1 times two U1 symmetries, and there is a charge conjugation. And going from here to here, the charge conjugation is gauged, and the two U1 symmetries become cosine symmetries. But now, what I want to claim is that on every point, in particular the rational point, rational radius, there are more continuous non-invertible symmetries, even just on the circle branch. Okay, and to see that, you just need to find this 1,0 or 0,1 operator at the end of the L, some topological line L. And here, the L is some topological line which generates the U1 momentum times U1 winding symmetry. And you can try to classify the operators in the twisted sector of this U1 times U1 symmetries. So it's easy to see because the operator takes the form of e to the I alpha phi times e to the I beta theta, where phi is the compact boson and theta is the dual boson that you get after doing the T-duality. And the alpha and the beta are the U1 valued parameters. Turns out that when alpha and beta when they are integers, then this operator is a local operator. They are not attached to arbitrary topological line. And you can work out the scaling dimensions, h and h bar equals to, there's some expressions. There are some expressions, and in general, for alpha equal to beta don't equal to the integers, then they are generated topological operators. They are generated operators, but in the twisted sectors. And you can also work out the scaling dimensions. And when you demand them to be 1,0, then you can solve for what value of alpha and beta. And it turns out that for each value of R, there are two values of alpha and beta which satisfy this equation. They are like this. The operators are like this. R times phi plus I theta over R, and J minus R equals to minus R phi minus I theta over R. And this is attached to the line L momentum 2 pi over R, L winding 2 pi times R. And this is attached to L minus 2 pi over R momentum, L winding 2 pi times R minus. Yeah. Okay. So from this, you immediately see that there are continuous non-invertible symmetry because these are the 1,0 operator in the twisted sector. And in the special case, when R equals to 1, you see that these operators are gone. And this current becomes local current, local 1,0 operators. And this is precisely the additional two additional currents which combine with the original momentum and the winding current to generate the SU2 times SU2 symmetry in the Wezumino-Witten model. Yeah. And in the case when R is not 1, but is a P over Q, then you see that it turns out that these operators, like R equals to 1 and R equals to P over Q, they are related by gauging. And it's precisely this gauging that makes the local current over here to be non-local current over here, which are these ones. So these operators are precisely constructed using the coset or the gauging construction that I mentioned earlier in the second part of the talk. Yeah. So from this perspective, all of these operators, all of these continuous non-invertible symmetries are not beyond the gauging construction. Yeah. So, but then we need to find more examples. So another example that
May I ask another
the
question?
yeah
Uh,
yeah
so in the rational radius, we also have the T-duality defect. Are you saying that there are new non-invertible defects, or they are related to the T-duality defects in the SU2
uh,
case?
so in this special case, so in
So
the
yeah,
T-dual, oh,
sorry,
you mean the
sorry, not in the,
non-invertible T-duality?
yeah. I mean that
Yeah,
case.
yeah,
In the
yeah. That's
rational
a
radius,
that's a good point. We haven't worked it out because for that case, in that case, we have to work out the um. Yeah, that's a very good point. Because in here, we want to find this twisted sector operator attached to
Mhm,
some line L, and we
mhm,
restrict this L to be these two U1s. But now you
mhm.
ask what happens if this L is a T-duality topological operator, right?
Yeah, kind of.
So in the
What's the role of that?
yeah, so in the case when this R is equal to 1, then this L is invertible. So you have a invertible T-duality symmetry. And when this R is not equal to 1, then this L is non-invertible. So you have a non-invertible duality operator, duality symmetry. And you can ask uh, what happens to this operator living at the end of the duality operator.
Yeah,
And actually, there is a paper exactly today, or maybe for you
I saw
yesterday,
it. It was
by
today.
Siwei and Shuhan. Yeah, they
Mhm.
work out precisely the operator spectrum of living at the end of the
Yeah,
T-duality defect.
yeah, I
Yeah,
think,
yeah, that would be
yeah, I think they were
interesting.
doing it in Maxwell. They have these strings at the
They
end of the
also have
duality defect.
they also have a example of the compact boson, which is exactly this example.
Ah, okay. I
Yeah,
see.
so
I'll check that
so
out
it
in
will
more
be
detail.
interesting to yeah. Okay. Uh, I don't have too much time, so maybe let me go for another one example, then I'll stop. So the next example is just the SEO2 level 1, level K, Wentz-Wiener-Witten model. And in this model, we want to look for the current 1, comma 0 operator living at the end of some topological line L. But we don't have a full classification of this topological line, discrete ones especially. But we do know some, and those ones are the ones that commute with the SEO2 level K chiral algebra, and these are the Follindi lines. So we can talk about the case when this L is a Follindi line, and it's known that for SEO2 level K Wiener-Witten model, there are K plus 1 Follindi lines labeled by a lambda, where lambda goes from 0, 1, 2, etc. up to k. So let's label the line to be L lambda. And the classification of the operators, the primary operator living at the end of the Follindi line is also well known, maybe from the 80s. So the idea is that you know you can work out the partition function, torus partition function, for this SU2 level K model. You insert a Follindi line in the space direction. And you also know the partition function because you know how the lines act on the local primary operators. And then you do the modular transformation. And then from this configuration, you read off the spectrum of the states or the operators in the twisted sector. And this spectrum exactly is the spectrum of the lines at the end of the L. Okay, so this is the idea. So we can go through this exercise and try to find whether there is a 1, comma 0 operator, the primary operator, live in this twisted sector spectrum. And it turns out that there are infinite number of incidences of case where there are such kind of operators. And those comes in the sequence when k is equals to n plus 2 times n minus 1, where n bigger or equal than 2. And this lambda, this L, correspond to lambda with 2 times n. Okay. So when k satisfies this special relation, then operators for linear line L. Examples, non-trivial examples. So for example, the first incidence is when n equals to 2. So in this case, k equals to 4, and the lambda, so the topological line is L4. And the fusion rule of the L4 is Z2 fusion rule. So it's a Z2 line attached that attached to the J. And it turns out that this Z2 is gaugeable. And after gauging, you will get some SU2, SU3 level 1 with millimeter model. So in this case, this non-invertible symmetry that constructed from this non-local current is invertible. It belongs to this gauging construction. Okay, now let's look at another example. N equals to 3, k equals to 10. And in this case, the current is attached to L6. But this L6 is a satisfied non-invertible fusion rule. So this is a non-invertible fusion rule. And it turns out that this line can also be gauged away. And after gauging, you will get a spin 5 level 1 Resume-Noether model. So it means that this continuous non-invertible symmetry also belongs to the gauging construction. But in this time, the gauging construction is more non-trivial because you have to gauge a non-invertible line in order to map between the local current and the non-local current. And the next example is n equals to 4, k equals to 18. And this is the first, and in this case, the current is attached to L8. But it turns out that there's no way to gauge away this L8 while preserving the SU2 Cal algebra. So this is the first example that we know that possibly sits outside of the gauging construction. Well, in that case, we have to gauge preserve the SU2 Cal algebra. So we call it conditionally intrinsic continuous non-invertible symmetry. It's intrinsic because it does not come from the gauging. And the conditional means that our gauging should preserve the SU2 Cal algebra. We don't know, like maybe there can be, maybe it turns out, maybe it can happen that you can gauge away this line, which does not, and the gauging does not commute with the SU2 Cal algebra. That can also be possible. But so far, we cannot confirm that because we don't know the full set of the topological line that only preserve the Ferrell-Sorrow, but not the SU2 level K current algebra. Yeah, it turns out that this list can go on and on. And the next example is 28. And it turns out that you can also gauge away this L10 line, and which gives you a G2 level 1 K model. But when n is bigger or equal than 6, the situation is very similar to this case where the line cannot be gauged away while preserving the SU2 level K Cal algebra. So they are also conditionally intrinsic. Okay, so yeah, I guess that's my time is up. So yeah, maybe I should stop here. Yeah, thanks for listening.
Okay, thank you for the great talk. now we can get a couple of questions from the audience, if there are any. Okay, no one has questions. I have a question. So in these conditionally intrinsic cases, you
Hmm.
have some sort of an obstruction to gauging the lines, right?
Yeah, that's right.
Is it like an anomaly or like
Yeah,
why
yeah, yeah,
can't you
yeah.
gauge it?
Yeah, that's right. So the reason that uh we know like whether we can gauge our way in this line or not is that we can check whether this line belongs to some algebra, right?
Hmm.
So gauging just means that inserting an algebra in the original partition function. And once you insert an algebra, like you do some gauging, then the original SU2 level K partition function will become some other partition function. But because it preserved the SU2 level K algebra, so the gauged the partition function after gauging is also constructed out of these chiral characters, the SU2 level
Mhm.
K characters.
I
And
see.
the only difference is that these characters are recombined, uh, uh, but in a non-diagonal way.
Hmm. Okay,
But nevertheless, they have to be modular invariant.
I see.
So people have already classified all the modular invariants of the SO2 level K using the SO2 level K characters. And
I see.
this is called the ADE classification. So
Hmm.
we can just refer to this ADE classification table and see whether this line can be gauged that way.
I see. Okay. And I also have another question regarding adjoint QCD2. So many of these structures that you have are very relevant for the
Yeah,
level one, somehow with some conformal embedding. You can get an adjoint
yeah.
QCD from bosonization. So,
That's right. That's right.
like, can we gain further insights into the non-invertible symmetries of that model from your formalism?
That's a good question. At least so you know that people studied adjoint QCD with one flavor, and in that case, the theories are gapped, right? So, so in that case, I would not expect the existence of these continuous symmetries. The reason is that these continuous symmetries are all chiral, so these J's are 1, comma 0 operator.
Okay.
So in a gapped model, it's very hard to believe that there are like continuous chiral currents,
Hmm. I see.
chiral continuous symmetries. But
Okay.
with more than one currents, like more than one flavors of the joint fermions, then it's natural. Yeah, maybe there also exists this kind of exotic symmetries.
I see.
Yeah.
Sorry, can I ask a quick question?
Oh, sure. Yeah.
Yeah, sorry. Yeah, actually, I missed the first part of the talk. I think I didn't come at the right time.
Uh-huh.
But have you considered a nonlinear sigma model with Calabi-Yau targets as well among the
Um,
examples you considered, or is it something you're planning to do?
that's a good point. Um, so So you can carry on. Well, first of all, I'm not a string theorist, so I have no knowledge about this nonlinear sigma model with Calabi-Yau target space. So maybe can I confirm one thing which is
Yeah,
that whether this model, this theory is a conformal field theory or not, or it's
yeah.
just some
They're
random sigma model.
yes, they're supposed to converge in the IR to CFTs, and they're known explicitly
So
at some specific point in the moduli space of the target Calabi-Yau,
good,
where you get
good.
those Gepler
So
models, for instance. And
so in the UV, this model is
yeah,
not conformally invariant, right?
yes,
It's
yes,
just on
exactly.
sigma model. Yeah, so
Exactly.
the one
Actually,
point,
yeah.
good. Yeah, one point that I didn't mention is that in fact we don't have a proof for the topologicalness of these symmetries. in the non-CFT series.
Okay.
So you see that our proof of these continuous symmetries relies on this computing these quantities, and this Ln and Ln bar are the Ferrasol generators, and in the non-generic QFTs they don't have that. But nevertheless, we do believe that these symmetries do exist in the non-conformal quantum field series. So then if you believe that, then you can ask like whether do they exist in these Calabi-Yau nonlinear signal models. Yes. And the question,
because
I don't know the answer. Also on the other side, so another another aspect, so another point is that our way to find the symmetries, so these symmetries to find the 1,0 operator in the theory, in the twisted sector. The fact that you can characterize this operator as a 1,0 operator is that you use the conformal symmetries to to decompose it into left and right. And for generic QFTs, honestly, I'm not quite sure how to find what is the criteria to select the correct operator in the twisted sector. Like what operator shall we consider as the current? Maybe we can just check whether it's a conserved, like computing the conservation equation. But on the practical level, I don't know how to do that. Yeah.
Thank you very much.
Yeah, sure.
Okay, any other question? I guess not. Let me stop the recording. Sometimes people also ask questions after record.